Okay, so hello and welcome back. So in the previous video we talked a little bit about the concept of derivatives, and we came across this limiting process, which was basically the discussion that we had in the previous video was clear enough. We know clearly what we're doing. Basically, the process is, of course, the process is pretty clear. There is nothing vague about the process. But then, we had basically this situation where, for example, we had basically this function over here, and we took some point over here, and for example some point over here, and we wanted to find the average velocity between these 2 points, for example, based on the situation that we had in the previous video. And so we said that we had to find the slope of this line that goes through this point and this point. Then basically we got closer to a little bit to this point. We are moving. What we are doing, basically, we're moving from this point. We are moving closer and closer to this point to get more, basically, to make the value of the average velocity much closer to the value of the instantaneous velocity at this point. And then we said that basically the average velocity at between these 2 points would be basically the slope of this line. Then we got a little bit closer, and then we said that again the average velocity between these 2 points would be basically the slope of this line. And then we call this the limiting process until basically the point got as close enough to the point over here, which we could actually imagine that, or we could assume that the 2 points were actually exactly the same point, and then based on that we could say that basically the slope of the line becomes basically the slope of a line that is, for example, touching the graph exactly at one point, at that exact point, and that was the instantaneous velocity of that object exactly at this point over here. So that was the process that we went through, and that was called the limiting process. That was called the limiting process. Now this process actually does exist in mathematics, meaning that there is a process by which you can just simply get closer and closer and closer to this point over here, and then surprisingly enough, it's actually basically, we saw that when we got to very, very close to this point, which would be our goal, basically was get to the point itself, and then that would be basically a form of 0 divided by 0. The average velocity calculated was the form 0 divided by 0, which was called in mathematics is called the case of indeterminate. And basically the beautiful thing that the limit does is that it actually does take care of the the 0 divided by 0 case, and it will give you some answer in the limit. which is actually pretty amazing. That's basically what it does. So now what we want to understand in these few videos, because there is actually a couple of illustrations here that we need to go through in order to understand the process. What we want to understand in this video is how this basically process of limiting works, how the limiting process works, and then based on that we will basically derive a couple of formulas using algebra for the limit, and then we will also do a couple of things about, we will basically work a little bit on the algebra of limits, meaning that, for example, what is, if you have, for example, the limit of, for example, f of x as x tends to a plus the limit of, for example, g of x as x tends to a, is it possible to add these two limits together? Or if you have, for example, the limit of f of x, for example, as x tends to a times the limit of, for example, g of x as x tends to a, and there is also basically subtraction, there is also division, and so on and so forth. We will talk a little bit about that as well. And then once we have understood the limiting process in detail, in enough detail, then we will use that. Then we will use the process of the limiting process in order to derive some formula for the derivative. That's basically what we want to do over here. So let's get started with a couple of examples that will basically illustrate how the limiting process actually works. Okay, so now as the first illustration, let's see what the function basically f of x is equal to x squared looks like. So the function f of x is equal to x squared is a function basically something like this, meaning that you have basically, let's say that this is the y-axis and this is the x-axis, and this is, let's say, y is equal to f of x, and your function would look something like this. Now on this function you can see that as x gets very close to 0, as x gets very close to 0 from this side or from this side, y is getting very close to 0 over here on the y-axis. So this situation technically and mathematically, we say that the limit of f of x as x tends to 0 is equal to 0. That's basically the notation that we use for the limit, and also kind of the meaning of the limit, although we have not really defined limits properly yet, and we will not define limits in this chapter over here. It seems that the definition is not there, but there is a very rigorous definition for the limit that involves delta and sigma and epsilon and things like that we will, I suppose, that we will deal with in the next book in this series. The definition is not here. Right now we have to kind of take things basically a little bit, I mean, we are not going to define anything, and based on this situation, meaning that you can see that as x gets very close to 0, y is also getting very close to 0, and so Mathematically we describe this situation as the limit of f of x. This is y is equal to f of x is equal to x squared. We say that the limit of f of x, the limit of this function, as x tends to 0 is equal to 0. Okay. Now again we have not defined anything yet, but you can say that you can kind of say that the limit of f of x as x tends to 0 is to be thought of as the value of f of x the value of f of x should assume at x is equal to 0. So the limit of f of x as x tends to 0 is to be thought of as the value f of x should assume at x is equal to 0. That means kind of this basically kind of means that basically the limit of f of x as x tends to 0, you could say that it's equal to f of 0, the value that f of x should assume at x is equal to 0. That's the meaning of this. Now suppose that, so this was one thing, and these are all basically illustrations based on different situations using different functions, and then you will have to form some sort of understanding or opinion about the concept of limits, and no definition has been introduced here, so I'm not doing that either. But you will be able to have a fairly good understanding of the concept of limits based on these illustrations. So the next case that we have here is basically consider some function, for example g of x. G of x is equal to the absolute value of x, where x is not equal to 0. So normally if you had g of x is equal to the absolute value of x, you would have some function like this. You would have some function like this. I don't know if that's 45 degrees or this is what, anyway, it doesn't. So that is y, that is x, and these two lines over here, that is basically g of x is equal to the absolute value of x. So that means that whether you enter positive values for x or negative values for x, the function is going to, the absolute value function is going to give you positive values. That's what it means. Now, if you have g of x is equal to the absolute value of x, but x is not equal to 0, meaning that x is not a part of the domain of the function, you need to take x is equal to 0 out, meaning that you can show this with a circle, with a hollow circle, which is not a filled circle. This would be a filled circle, for example. This would be a filled circle, and this is a hollow circle. What this means is that basically x is equal to 0 is a part of the domain of this function, and what this means is that x is not a part of the domain of the function. So now So now what we need to, what we have is basically this situation: g of x is equal to the absolute value of x, and x is not equal to 0. So now consider if I have this situation over here. You see that basically g of 0, you see that g of 0 is not defined, is not defined in this function, is not defined in this function. Now if you compute the values of g of x for values of x very close to 0, we see that basically the value of g of x moves towards 0, meaning that if you get very close to 0, for example from this side, or very close to 0 from this side, for example, moving close to 0 from this side would be 0.1 or 0.01 or even 0.001 or 0.0001 and so on and so forth, getting closer and closer to this, to the x from this side, or getting closer to x from this side, meaning that for example something like you could start with -1 and then for example -0.9 or -0.99 or -0.999 and so on and so forth. As you enter these values into the function, these values are still defined, and the function would give you an output for these inputs. And for example, g of, for example, 0.1 would be equal to the absolute value of 0.1, which is equal to 0.1. Or basically g of -0.9, for example, would be the absolute value of -0.9, which is equal to 0.9. So these values are all defined. And when you get closer and closer to x from to 0 from both sides, you can see that as you get closer, y is getting closer to 0. So we say that the limit of basically g of x as x tends to 0 is equal to the limit of, for example, the absolute value of x as x tends to 0 is equal to 0. And of course you can see that on the graph of the function that the same thing is actually happening here. So formally, or in general, we can say that as x tends to a, f of x tends to some, for example, L, and then L is called the limit of the function f of x, is called the limit of the function f of x at a, which is symbolically written as the limit of f of x as x tends to a is equal to L. That's basically the whole situation over here. Okay, so that's that. Okay, so now let's suppose that you have a function, for example h of x. H of x is equal to basically x squared minus 4 over x minus 2. X is not equal to 2, because if If you set x is equal to 2, then you're going to get a 0 in the denominator. Also, you would get a 0 in the numerator, you would get 0 by 0. Now, if you compute the value of h of x for values of x very near to 2, but not at 2, so for example, you set the values of x very close to 2, you would get, for example, let's say that x is equal to, for example, 1.9. Then you would get h of 1.9 is equal to basically 1.9 squared minus 4 over 1.9 minus 2. Now 1.9 squared is equal to 1.9 times 1.9 is equal to 81, 8, 17, 0, and you have a 19 here. So you have 1 plus 7 is equal to 16, and that's a 3, 2 decimal places, 3.61. That is 3.61 minus 4 over 1.9 minus 2 is equal to negative 0.1. Now, I suppose that basically 3.6.4.3.9, negative 3.9, negative 3.9 over negative 0.1. So these two you can cancel out and you get a 30. No, that is, I'm sorry. I made a mistake here. 4 minus 3.61, 4 minus 3.6 would be 0.4, so that's 0.39. So that's negative 0.39. And over here you have negative 0.1. And then you would have basically times 10, you would get 3.9. So the value of the function at x is equal to 1.9, for example, is 3.9. And of course, if you enter x as basically 2 here, what you will get is basically h of 2 is equal to 2 squared, which is equal to 4 minus 4, and 2 minus 2, which is equal to 0 over 0. And that is again what we are talking about, that the indeterminate form, that is the indeterminate form, 0 by 0. And basically all that the whole concept of limit does is that it resolves this issue of 0 by 0 for you, and that's basically all that basically limit does for you. Now suppose that I set the value of x as, for example, suppose that I set the value of x as 1.99, very close, much closer to 2. Then h of 1.99 is equal to 1.99 whole squared minus 4 over 1.99 minus 2. So let's see, 199 times 199 is equal to 81, 8, 81, 89, 8, 9 plus 8 is equal to 17, 0. And then you have the same number, 1971, and 2 zeros, 199. And you'll get a 1 over here, you'll get 0, 1 over here. 18 plus 8 is equal to 18 plus 8 is equal to 26, 2, and then you have, this is 19, 1, and this is 3, and you have basically 4 decimal places, you have 3.9601. You have 3.9601 minus 4 over basically 1.99 minus 2. And so then you would have 3.9601 minus 4 is equal to so let's subtract 4.0000 minus 3.9601. We'll get a 3 over here, 10, 9, 9, 9, and 10. You'll get a 9 over here, a 9 over here, a 3 over here, a 0 over here, and a 0 over here. And that is negative 0.0399 over basically 1.99 minus 2, which is equal to negative 0.01. Negative 0.01. And okay, so now if I multiply this by a factor of 100, what I will get over here is 3.99. 3.99 over, so you see that the value of the function becomes 3.99 at x is equal to 1.99. And so you see that as I'm getting closer to 2, the value of 2, y is getting closer and closer to the value 4 basically. Now if you go the other way around, meaning that basically if you approach 2 from the left, meaning that for example if you calculate h of, for example, from the right, if you approach 2 from the right, you will get, for example, h of 2.1. h of 2.1. So h of 2.1 would be, for example, 2.1 squared minus 4 would be 2.1 squared minus 4 over 2.1 minus 2. 2.1 minus 2. And that gives you basically 21 squared is equal to 21,042 and 441, 2 decimal places, 4.41 minus 4 over 2.1 minus 2 is equal to 0.1, which is equal to 0.41 over 0.1, which is equal to 4.1, very close to 1. If you go for example 2.05 for example, or if you go for basically, so if you get 100th of a or 100th of a unit away from 2 from the right, would be 2.01. so h of 2.01, that would give you basically 2.01 raised to the power 2 minus 4 over 2.01 minus 2, which is equal to 201 times 201, 201, 0, 201, 0, and another 0, and then 402, 10404, and you have 4 decimal places, 4.0401. 4.0401 minus 4 over 0.01, which is equal to 0.0401 over 0.01, which is equal to 4.01, very close to 2. So you see that as I'm getting basically closer from right and left to 2, that the values of h of x are getting closer and closer and closer to 4. So and if you take a look at the graph of the function, x squared minus 4 x minus 2, x squared minus 4 over x minus 2, if this is the value of h of x, then the graph of the function would be, for example, at x is equal to 0, for example, you're at negative 4 over negative 2, which is basically 2, and at x is equal to, for example, negative 2, you are at negative 2 squared minus 4 over negative 2 minus 2, which is equal to 4 minus 4 over basically negative 4, which is equal to negative 4, which is equal to 0. So at negative 2 you're at 0. So then what that means is that one of the points is 0, 2, and one of the other points is negative 2, 0. This point over here, and your function goes through these 2 points. This is the graph of the function. This is y and this is x. Now we said that x is not basically x is not equal to 2. That means that you have to take x is equal to 2 out of the domain of the function. So I take this out, and so that becomes the graph of the function. Now the function is not defined at x is equal to 2, so h of x is not equal to 2 means that h of x is not defined at x is equal to 2. But as I'm getting closer to x is equal to 2 from the right or from the left, the function is tending towards this point, which is 2, 4. At 2 you are at basically this point is supposed to be 4, so this is 2, 4. So and as you move towards 2 from the right, or you move towards 2 from the left, the function is getting closer and closer to this point, 2, 4. But the function is not actually defined as at 2 is equal to at x is equal to 2. And so even based on the graph of the function, you can see that the limit of this function, you can see that the limit of h of x as x tends to 2, which is equal to the limit of x squared minus 4 over x minus 2 as x tends to 2 is equal to 4. So that's basically that. Now, in all of these illustrations that we had so far, basically we had this example over here where x was, for example, f of x was equal to x squared, and we wanted to find the limit of f of x as x was tending to 0. And you can see that as you're getting closer to 0 from the right or from the left, f of x is tending to 0, meaning that it doesn't really matter from which side you're getting close to x. Your f of x at that point is basically getting closer and closer to 0, and so you say that the limit of f of x when x tends to 0 is equal to 0. Again, in this example, it doesn't matter from which side you get closer to x. Again, at that point, f of x is tending to 0. In this example, you can see that it doesn't matter from which side you get closer to 2. at that point f of x is getting closer and closer to 4. So basically what that means is that there are actually two ways to get closer to a, meaning that when you write, for example, when you write the limit of some function f of x as x tends to a is equal to L. L is the limit of function and a is the number that x basically tends to, which is, for example, in this case is for example positive 2. And there is always, well, not always, but most of the time, there is basically two ways to get close to 2, either from the right or from the left. So this gives you basically two different things, or in some cases it could actually give you two different values for the limit of the function, meaning that when you're getting close to 2 from the right, you will get something called the right hand limit. You will get something called the right hand limit, and from when you get closer to 2 from the left, you will have something called the left hand limit. The left hand limit. Now you get two basically values you get two different values for the right hand limit and for the left hand limit. For example, in this case, as we got closer to 2 from the left, the value of the function seemed to be tending to 4, 3.9 and 3.99. So then I can say that the limit of h of x when x tends to 2, for example, from the left is equal to 4. This is called the left hand limit. And also when we got closer to 2 from the right, the value of the function seemed to be tending to some value 4, for example, which I can write limit of h of x when x tends to 2 from the right is equal to 4. Now basically they have defined the concept of limit in such a way that the limit of a function is defined. The limit of a function f of x at x is equal to a is defined if the limit of f of x when x tends to a from the right is equal to, for example, first of all, this limit exists and is equal to some number, for example, to some number b, for example. And also if the limit of f of x when x tends to a from the left exists, sometimes the limit simply does not exist. The limit exists and is equal to some number, for example, to some number b, meaning that the limit of a function f of x at x is equal to a is defined if the limit of f of x when x tends to a from the right is equal to the limit of f of x when x tends to a from the left and that is equal to the limit of f of x, when x tends to a, which is equal to L. That is basically the whole story behind the limit of a function. So you can say that the limit of a function f of x at x is equal to a is defined if the right hand limit exists and is equal to some number b, if the left hand limit exists and is equal to some number b, and those two limits are equal to some unique number and to just one number, meaning that the two limits are actually equal. So then you can write the limit of f of x as x tends to a from the right is equal to the limit of f of x when x tends to a from the left, and that is equal to the limit of f of x when x tends to a, and that is equal to L, and that means that the function that the limit of the function at some point a is equal to L, and it is defined and it exists. Now we have a question over here, which is basically a function which has basically two different parts, and we will basically talk about what we just talked about here, the right hand limit and the left hand limit. We will see the example illustrating basically the same concept here. Okay, so now we have one more illustration here before we do a short summary. And suppose that you have, for example, this function over here, which is f of x is equal to, for example, 1 if x is less than or equal to 2, is less than or equal to 0, I'm sorry, and the value of the function is 2 if x is greater than 0. So this function is basically something like this, meaning that you have basically the value of the function is 1 is if x is greater than or equal to 0. So you would have something like this, and the value of the function is 2 is if x is greater than 0. So this is f of x is equal to 2, and this is f of x is equal to 1. Now, but of course you need to make some changes here, because when x is, basically this output 1, f of x is equal to 1, is related to when x is less than or equal to 0. So less than or equal to 0, you will have a filled circle over here, and over here you will have a hollow circle, indicating that over here x is only greater than 0, and over here x is less than or equal to 0. So that means that basically the output of this function at x is equal to 0 is 1. As you can see, the output of the function at x is equal to 0, f of 0 is equal to 1, as dictated by this clause over here. Now, if you try to find the limit of this function as x tends to 0, this is one of those interesting. I mean, this is an interesting illustration, which means that when you write the limit of f of x when x tends to 0 from the right, for example, you have to approach 0 from the right, meaning that you have to go along this line over here, which is, and the value of the function at very close to 0 along this line is going to be f of x is equal to 2. And if you take the limit of f of x when x tends to 0 from the left, is going to be 1, because you have to go along this line dictated by, for example, this clause over here. The other one is dictated by this clause. So what that means is that in this case you can see the right hand limit and the left hand limit both exist. They do exist, but their values are different. Over here you have a 2 and you have a 1. And since we can say that the limit of f of x as x tends to 0 does not exist, so then you can say that the limit of f of x when x tends to 0 does not exist. And the reason is that because the limit of f of x when x tends to 0 from the right is not equal to the limit of f of x when x tends to 0 from the left. Even though the function, even though f of x is defined at x is equal to 0. So that is another example. Now, as a short summary, we say that the limit of f of x when x tends to a from the left is the, let me write it down over here. So we say that basically the limit of f of x, and this is just as a summary. So we say that the limit of f of x as x tends to a from the left is the expected value of f at x is equal to a. This is the expected value of f at x is equal to a. Given the value of f, given the values of f, given the values of f near x to the left of a, near x to the left of a. Of course, this doesn't near x to the left of a, meaning that for example, if x is equal to a is, for example, x is equal to 4, for example, that means that near 4 to the left of 4. That's what is meant by this sentence over here. And we say that the limit of f of x when x tends to a from the right is the expected value of f, that is the expected value of f at x is equal to a, given the values of f near x, given the values of f near a, given the values of f near x, for example, you could say, because x is equal to, it doesn't really matter, to the right of a, to the right of a. This value is called, so this value is called the left hand limit. This value is called the right hand limit. This value is called the right hand limit. Now, if the right hand limit and the left hand limits coincide, we call that common value as the limit of f of x at x is equal to a. So if the limit of f of x when x tends to a from the left is equal to the limit of f of x when x tends to a from the right, and that is equal to L, for example, that value we call it the limit of f of x. We call it the limit of f of x at x is equal to a, or as x tends to a basically, which is denoted by the limit of f of x when x tends to a. So that's a short summary of basically what we did so far.